And we are moving to the next presentation, which is given by Lucas Rubidoux on the fly detection of Bloom filter, false positives, and application indexing k-mers with their abundances. So, Lucas, please go ahead.
Okay.
But no, sorry, because I'm seeing on YouTube that, okay, no, the slides are there. Okay, please go ahead. Thanks.
Okay, so everyone can see my slide. Okay.
Yes, please go.
So, hello everyone. My name is Lucas Robidou. I'm a PhD student. I just started my PhD like 4 months ago. So what I'm going to present is just small ideas and not fixed things. So if you have any input, I'll gladly accept them. So my talk is about query time filtration of false positive camera and multi-filters that I'm going to introduce later. So I'm going to first remind you what Bloom filters are, then how to identify false positive results of those said Bloom filters, and I'm going to introduce you multi-filters. So a Bloom filter is a data structure that is designed to tell whether an element called, for example, W is present in a set. If W is present in that set, the query returns true. If not, if the element is not present, the query may still return true with a probability of epsilon. That's the definition of a false positive, and we would want epsilon to be the lower possible to reduce the number of false positives. So some characteristics of said Bloom filters. The only possible answers are Boolean, yes or no. You don't have like maybe yes, maybe no, no possibility of having a probability attached to your response. And we can't count camera as said just before, like integers. No, it's only Booleans. And if n represents the number of elements stored, this formula gives you the size of your Bloom filters, depending on epsilon. Of course, the lower the epsilon, the your Bloom filter. But quite interestingly, the memory grows linearly with the number of elements stored. I'm going to use that later. So my method, our method to identify false positive results is based on our context. It only works with our context. The context is the query of a Bloom filter that contains genomes. When you query a genome on a Bloom filter, you extract every possible camera inside your queried sequence. You query each one of your camera, and then you can compute the similarity between your sequence and your index. So I'm going to show how it works. Very basically, you have an index sequence that you want to index and a query that, well, you want to query. So in an ideal world, you could take a perfect filter, let's say a hash table, for example. You store each camera of your indexed sequence into your hash filter, hash table, sorry. And then you take your query, you extract every camera, and you make a query for each of your camera. So let's test the first one, and it's a negative. The second one is negative, the third one is a positive, and so forth and so on. And so you can compute the similarity between your query and your index sequence. But in the real world, to gain some space, some memory, we use Bloom filters. And as you can already know, Bloom filters have false positives. So if I use a Bloom filter, then I have a false positive, a camera that is not present but is still found inside. And that's a problem. We would want to get rid of those. And to get rid of those, I need to introduce you some definitions. What I called a positive camera is a camera that is found in a Bloom filter. So it might be a false positive, we don't know yet. I'll just call it a positive camera. The neighborhood of a camera are cameras that are located on the left and on the right of a given camera. The previous camera on the next one. immediately next one. Then Z positive stretch is a stretch of Z positive neighbor. I mean, each neighbor have a camera. If camera have a neighbor that is positive, at least one, to continue the stretch. And one isolated camera is a camera that is like one positive stretch, so no positive neighbor. So in our query, we have 3 positive stretch and one isolated camera, as you see there. And we would want to get rid of the false positive. Looking at that query, you can guess that there's very high chance for a false positive to be isolated. I mean, you have each of his neighbor is very not likely to be positive if it's a sequence of false positive. So the main idea is to get rid of those said false positive by fixing Z, the number of the length of the stretch you want to get rid of. You extract every camera, you query each camera on your Bloom filters, and if a camera is not part of at least a Z positive stretch, you filter it out. You consider it's a negative, you correct your Bloom filter, and then you can compute the similarity. We tried that approach with Bloom filters of 4% false positive rate and K equal to 32. We indexed 2 Escherichia coli, 1 Listeria phage, and 1 penicillium, and we queried another Escherichia coli. We fixed Z to 6, and thanks to that, we were able to decrease the false positive rate from 4%, the original false positive rate of the Bloom filter, to 0.005%, which is a gain of about 800. However, the price to pay is that we kind of turn the false positive into a false negative rate of 3.6%. So in that figure, in abscissa, you can see the load factor of the Bloom filters, the number of elements per bit. And I plotted the false positive rates of a theoretical Bloom filter, which is in red, and the false positive rate of the queried time filtered Bloom filter, sorry, in green. And you can see that our solution is pretty robust, meaning that you can increase the load factor of your Bloom filters without increasing your false positive rate. And you see that the false negative rate is also fixed at about 4%. So yeah, those are our preliminary results on query time filtration. Then, if you have any question, please ask them now, as it's something that's quite important for the next slides. Okay, I don't know how you can ask a question anyway. Sorry. So on to the next part, multi-filters. So if you remember what I just said about Bloom filters, the only possible answers are only Booleans, yes or no. And we would want to be able to count abundance of our cameras. So the basic idea here is to store one Bloom filter, is to use one Bloom filter per abundance. So we end up having a lot of Bloom filters. Comparing to Bloom filters, multi-filters is composed of lots of multiple Bloom filters, and each camera is stored to the sub-Bloom filters corresponding to each abundance. So how do you use that? Well, you take each one of your camera, and instead of doing one query to Bloom filters, you do multiple query on each sub-Bloom filters. So you end up having way more query to Bloom filters. So camera by camera, you make all your requests, and that way you can compute the abundance. Once again, as it's composed of Bloom filters, you may have some false positive, like at the end of that query. So yeah, that's basically the output of a query. You can see that it's not yes or no anymore, it's numbers. So that's the first step to be able to count abundance. However, compared to Bloom filters, as I just said, you have to make a lot of queries, one query per sub-Bloom filters. So you end up having way more chance to have a false positive that arrays in one of your sub-Bloom filters. One possible solution would be to lower the false positive rate of each one of your sub-Bloom filters. So the query made of multiple sub-queries would end up having a epsilon just like the original Bloom filters. But if you do that, each one of your sub-Bloom filters will end up having the same size as your original Bloom filter. So say if you want to index 100 abundance, or you want to allow yourself to store from 1 to 100 abundance, you would end up having 100 times more memory than the original solution. So that's not a good solution here. That's not a practical solution. What we need is the way to get rid of those false positives without requiring more memory. Unfortunately, we have that solution. It's filtration. So I take that algorithm again. When you want to store the abundance, when you want to query, your abundance, you extract every camera. You query each camera with each one of those sub-Bloom filters. If a camera is not part of a Z-positive stretch on at least one sub-Bloom filters, you consider it as a negative and you filter it out. Else, you might end up having a conflict between two sub-Bloom filters. Two sub-Bloom filters might say, okay, I just saw that camera. So you have to choose between both. And the way to choose is to select the filters for which the number of stretch, the higher stretch is maximized. And then you can compute the similarity with the abundance. So in that figure, I plotted in the abscissa the position of the camera in the query. So at the top left, you have the start of the sequence, and at the right, you have the end of the subsequence that I plotted. In the blue dotted line, you have the truth, what you would expect to have if you have a hash table. So it's here in practice that's not possible to have a hash table that is that large. That's why it's only a part of the query that is represented here. And in blue or light blue, those are the positive that is kept by camera filtration, and in red that are the false positive according to the query time filtration. So if I remove all the red points, you can see that match pretty much the blue dotted line. So we removed a lot of false positives without losing too much of true positives. And indeed, if you look at that figure again with multi-filters, you can see that the false positive rate is once again very low at about 0.004%, and is keeping very low even if you load the filter a bit more. However, once again, you will pay that by paying a false negative rate of 4%. So the take-home message is that by using one Bloom filter per abundance and camera filtration, we can index camera along with their abundance without paying more memory, since it's linear in the number of elements you stored only. And you keep storing the same number of elements. That way we can achieve 800 times less false positive than we would have expected using naive bloom filters, but the price to pay is about 4% negative rate, which is, well, 4% than naive bloom filters. Thank you for your kind attention.
Thank you very much for your talk. So it's question time. I can see the first question. What about running times?
Okay, yeah. From what I see, the multi-filters plus camera filtration is about 3 times less efficient at running time. You take 3 times more time to execute your request. But the thing is that, as I said, it's only preliminary results, and it was written in Python, which is not known for being the quickest language. So I expect to gain some time at running time in the future.
Yes, and talking about development, future developments.
Yes.
Have you also tried different false negative rates? Is it possible to achieve, with a different trade-off between time and memory usage to achieve a different false negative rate?
Your original the original bloom filters doesn't have any false positive rate. You can change that. It's 0%.
No, but I mean, with your approach, is it possible to use it with a smaller false negative rate? Yes, maybe with a longer runtime or something like that.
Yes, if you change the Z, the length of the stretch of positive, if you reduce it, you're going to filter less results. So you end up having a higher a lower false negative rate, but a higher false positive rate.
Okay, thanks. Another question. Have you characterized the sequence properties on which the false negative ratio depends and how it changes with different sequences? It seems like it's related to the divergence between the query and the index sequence.
Can you repeat the question? Sorry.
Okay, if you know when on the sequence properties on which the false negative ratio depends, and how the false negative ratio is affected by the fact that the query sequence is much different from the one that you have indexed at the beginning.
Well, actually, the false negatives that are not filtered out are false negatives that are part of a long stretch of false positive, right? Since I only filter out false positive part of a small stretch of positives. And if you take a Bloom filter, when you make a query in it, you have epsilon% of having a false positive, but epsilon times epsilon of having 2 false positive, and epsilon times epsilon times epsilon to having 3 false positive. So say you fix epsilon to 10%, then having a long stretch of 6 positive camera is 1 on 10 to the power of minus 6, right? Well, it decreases with epsilon, but it doesn't depend on the query you make actually, because the false positives are here when there's nothing, basically, if there's something that's a true positive. So it happens in between the holes of your sequence. So you can't, there's no property here to check.
Okay, thanks. I see another question. Bloom filters have been implemented in the de novo genome assembly tool EBIS version 2, for example. Could multi-filter be an improvement to reduce false positive?
Well, I don't really know about what the person is talking about, but as long as you have the property that one camera is likely to be found with another camera. Like the only property that you need is that one positive camera is likely to happen near one another positive camera. As long as you have that property, it can be well applied, I think.
Okay. Thank you again. Thank you very much.